receptors, and when we get into chapter 6, we'll see a lot of protein receptors and talk about the interactions of the ligands there. But transporters have to be proteins also, okay? And they are, just think of them as molecules that protect the transport of something across the membrane. They hide the fact that this thing that's moving across has a charge or it's polar. So it's a way to facilitate its movement, to facilitate its diffusion. Okay? Now, because these are proteins, let's not forget this, right? Because these are proteins here, we have to consider that they have to be able to bind to whatever they carry, right? So any of these carrier proteins, any of the ones that we're talking about, whether it's a channel or carrier protein or whatever, they have specificity. Right, what else?
Affinity.
They have affinity. They show competition among substrates that have similar structure.
Saturation.
And they'll exhibit saturation, meaning that, you know, diffusion can only occur so rapidly until all of these things are being used. And as soon as all of the proteins are being used, they reach saturation. So all of these things are going to, these protein ligand things that we talked about in the context of just general interactions and enzymes, also have a role here. And it's important to realize that if we're talking about mediated transport and carrying things across, we have to keep those four kind of properties in mind. Channel proteins, these are used for things that are pretty small. We make a little channel through it. We would call them ion channels. So what goes through an ion channel? Ions. These ion channels show specificity, meaning that there's probably hydrogen ion channels, right? And there's probably calcium channels, and sodium channels, and things like that. There are some examples of channels that are, for example, a monovalent cation channel, which means anything with a +1 charge can go through it. But guess what? Some things will go through, like for example, there's one that lets the diffusion of both sodium and potassium go through it, but it has a higher affinity for sodium, so sodium passes more easily, right? So I mean, that's the competition part of it. It will preferentially allow sodium over potassium. These channels can reach saturation, right? At some point, it doesn't matter how much or how steep of a gradient you have, the rate of transport is dependent upon how many channels you have. So all of those things apply here. Are these channels always open, or should they have gates on them?
Gates.
They should have gates, right? Because if they're always open, what's the point? Right? Then we wouldn't be able to have a chemical disequilibrium. So these gates are going to be open and closed under different scenarios. There are chemically gated channels. What does that mean? That means under the presence or absence of a particular chemical, the gate will open or close. If it binds calcium, the gate opens. And then something goes. There are mechanically gated channels. That means that something physical disturbs the structure of the membrane. We push on it, we pull on it, or whatever, and that makes the channel open or close. And we'll see that a number of these gates are voltage gated. Under certain electrical stimuli, they'll open or close. And in fact, that's going to be important for us when we talk about electrical transmission in neurons and things like that. So the bottom line is that these gates open and close. When they're open, you get flux. When they're closed, you don't get flux. If substances move into the cell, we call that influx. If ions move out of the cell, we call that efflux. Okay, so influx into the cell, efflux out of the cell. Ion flux. So we get ion flux through these channels.
Dr.
Yeah.
So will be cofactors be considered as like chemical or mechanical?
In this regard, like for example, if it was a calcium that bound to it, would we call that a cofactor? That's a good question. I mean,